Have you ever really stopped to think about what music is? I mean, at its most basic level, it's just vibrations, wiggles in the air. So how do those simple vibrations turn into the complex, beautiful harmonies that we all love? Well, today we're going to dive into the hidden physics that turns a vibrating string or a column of air into a full-blown symphony.
So let's start with a question to get our heads in the game. Think about a guitar. You've got one single string, right? But from that one wire, a musician can pull out this huge range of distinct, perfect notes. How in the world does that work? It's not magic, it's physics. And by the time we're done here, you are going to understand exactly how it happens.
All right, the very first piece of this puzzle is a really cool phenomenon known as a standing wave. It's the foundation for, well, pretty much everything we're about to talk about. And honestly, it's kind of a beautiful illusion.
Okay, so imagine you have two waves moving toward each other. In this top picture, they're perfect opposites. The peak of one wave lines up exactly with the valley or the trough of the other. And when they meet, poof, they completely cancel each other out. We call that destructive interference. The result is nothing, just a flat line.
But what if those two waves line up perfectly? You know, peak to peak and trough to trough, just like you see here. Well, instead of canceling out, they build on each other. They reinforce each other to create one single, much bigger wave. And that, you guessed it, is called constructive interference.
So what's this got to do with a guitar string? Well, when you pluck it, a wave travels down to the end, bounces off, and comes right back, interfering with the waves that are still coming down the string. All that constructive and destructive interference creates this really special pattern. It's called a standing wave because it looks like it's just vibrating in one spot, even though it's actually made of two waves zipping in opposite directions.
Okay, so how does this cool illusion of a standing wave actually make real music? Let's connect the dots now from this abstract physics idea to what's happening on an actual instrument.
Take a look at this. This is the simplest possible standing wave that can fit on a string that's tied down at both ends. See? It's just one single arc. This vibration produces the lowest possible note the string can make, its bass note. We call this its fundamental frequency, or you can think of it as the first harmonic.
Now here's where it gets really amazing. A string can't just wiggle however it wants. Because it's fixed at the ends, the only waves that can actually survive are the ones that fit perfectly onto that length. And as you can see in this chart, this creates a whole series of allowed patterns, 1 loop, 2 loops, 3, and so on. We call these patterns harmonics. And just look at the frequencies. They're perfect whole number multiples of that fundamental one. If the first is F, then the next is exactly 2F, then 3F. Isn't that wild? It's this beautiful mathematical order just hiding in a simple vibration. And we also call these higher harmonics overtones. Just note, the second harmonic is the first overtone, the third is the second, and so on.
And listen, these aren't just suggestions. These are the laws of physics for that specific string. Any other vibration you try to create, anything that doesn't fit one of these patterns, will interfere with itself and just fizzle out almost instantly. These are the string's natural frequencies. They're the only sounds it truly wants to make.
But why? Why does this string only want to vibrate at these very specific frequencies? The answer is a really powerful concept in physics and in life called resonance.
You already know exactly how this works. Think about pushing someone on a swing. You can't just shove them whenever you feel like it, right? To get them to go higher and higher, you have to time your push perfectly with the swing's own rhythm, its own natural frequency. That is resonance, right there in the playground.
And that's exactly what resonance is. It's what happens when you add energy to a system at a frequency it already likes to vibrate at. It's like a secret handshake. When the frequencies match, the energy transfers super efficiently, and the vibration gets huge. So when you pluck a guitar string, you're not making one sound. You're giving a little burst of energy to all of its natural resonant frequencies at once.
Okay, so we've pretty much mastered strings. But what about instruments that don't have them? You know, like a flute or an organ pipe? Well, as we're about to see, the exact same principles of standing waves and resonance are at play. This time, though, the thing that's vibrating isn't a string, it's a column of air.
So let's look at these two scenarios. On the left, you've got a tube that's closed at one end. Think about blowing across the top of a bottle. And on the right, you've got a tube open at both ends, like a flute. Just look at them. The shape of the simplest standing wave is totally different for each one. And that's because the physical rules of the game are different. Let's break this down. In a closed tube, the air can't really move at the sealed end, right? It's a dead end. That creates a point of zero vibration. We call it a node. And because of that physical limit, only the odd-numbered harmonics can form, the first, the third, the fifth, and so on. But in an open tube, the air can vibrate like crazy at both ends. That allows all the harmonics to form, just like on the guitar string. And this, right here, is a huge reason why a clarinet, which acts like a closed tube, sounds so different, so much more mellow than a flute.
And this isn't just theory, you can actually use this stuff. For example, if you find that a closed tube makes its first, lowest note when it's 18 centimeters long, you know for a fact that that length is exactly 1/4 of the sound wave's full wavelength. So you can easily figure out the full wavelength. It's just 4 times 18, which is 72 centimeters. This is literally how instruments are designed and tuned.
Okay, we're almost there. Just one final piece to this whole musical puzzle. We know how a string or an air column makes a specific note. But why does that same note, let's say a middle C, sound so completely different when it's played on a piano versus on a violin? Why does every instrument have its own unique voice?
This is the sound wave from a tuning fork. It's about as pure as a sound can get. It's almost all fundamental frequency, with very few other vibrations mixed in. It's a clean, simple sine wave, and it makes a really pure, almost electronic-sounding tone.
Now, compare that super pure tone on the left to the waveform from a violin on the right. They're playing the exact same note, but look at the violin's wave. It's way more complex, more jagged, more interesting. That complexity is what our ears hear as richness and character. So the question is, where does all that complexity come from?
And here is the secret. When an instrument plays a note, you're never just hearing that one fundamental frequency. You're actually hearing a rich combination, a whole cocktail of the fundamental plus all those other harmonics or overtones layered on top, all at different volumes. This specific recipe of overtones is called timbre, and it is what gives every single instrument its unique sonic personality, its color.
So this really brings it all home. Those standing wave patterns we were looking at, they're not just isolated possibilities. You can think of them as the sonic ingredients that are available to an instrument. The note you actually hear is the final recipe, that unique blend of all those ingredients that defines the sound of a violin or a piano or even the human voice.
So there you have it. From a single vibrating string all the way to a complex symphony, it all comes down to the simple, elegant physics of standing waves and resonance. The next time you listen to your favorite song, you'll know what's really going on under the hood. And that leaves you with one last thing to think about. Now that you understand this principle, where else in your world can you spot resonance at work?